Next speaker, Sergiy Maksymenko. Please.
Thank you. Let me share the screen. Well, okay. Can you see my screen?
Yeah.
Yes, good. Well, so my talk is about topological actions of wreath products, and the general statement. Maybe I will just briefly formulate what I will be talking about. Is that I will define and recall the notion what is a wreath product of two groups G and H, and then I define consider special actions of this group on some topological space X, and the general question, the general result which I obtain is that computation of the fundamental group of the quotient space. That will be the general result, and after that I will explain the applications and maybe motivation of why it was this statement appeared. So let me first recall what is the wreath product of two groups. I will start from example. For instance, consider this table of this kind. Let me here something like this. So you see that here is 5 and here is 4 cells, and consider the group. Let the group W will be a permutation of cells preserving columns. So we just make any permutation of these squares, but we interchange them in the following way. So first we interchange columns, and after that we can make any permutations inside each column. And this group, the group of these permutations, is what is called the wreath product of S4 with S5, where Sn is the permutation group of the set of n indices. So we have a set of numbers, and this is just a permutation group of this set. This group can also be defined just viewed in the following way. So consider this graph. Let me show this graph. Here is just 5 edges from one edge, and here we have also 4 edges. And do you see that actually the group of permutations of this kind is the same as a group of automorphisms of this graph? So it is the same as the group of automorphism of this gamma, because this is the same. First, any automorphism should make some permutation of these trees, and they correspond to columns. And also in each of these trees, one can additionally make any permutation of these edges, and this is the same as permuting of these columns. So this is where the wreath products, and it is called wreath product of these two groups with respect to special action of this S5 on the set S5. But let me how to imagine this group. Let me describe it in some so to see how the elements of this group are defined. Namely, let us look for instance at this. So first of all, we have an element belonging to beta belonging to S5, and it corresponds to permutation of these trees. And after that, at each level, I have an element belonging to, maybe I take them too much, but actually each of them belong to S4. So every permutation, every automorphism of this graph is actually given by this collection of permutations. So I need 5 permutation elements from the group S4 and 1 element from group S5. And finally, this means that how to formally define this group. I should do this collection can be viewed as a map from the group S5, from the set S5 to the group S4. Yeah, just here. So if I enumerate these positions by 1, 2, 3, 4, 5, then actually these elements is just the can be regarded as the values of some function alpha on this set. And also I need some element from here. So in general, this group S4, S5 over X5 is by definition the set of maps from the set this X5 into the group S4, and this will be the so-called, this is a group with respect to the point-wise multiplication, and it is a semi-direct product with this group S5. So this is the formal definition. What is a wreath product? And in general, if we consider what is the general definition of wreath product is the following. So suppose we have a group G which acts on some not G but H. We take group which acts on some set X, and then also group G, then their wreath product G X H is by definition the set of maps from X to G, semi-direct product with H. And the operation is in this group is given in the following way. So if I take here element alpha, so I just take two elements. Let me take two elements from this set. So I take a map from X to G. This is alpha, and here element H belonging to H. Then I take another element, say beta. Again, this function into G, and another element H prime. So this will be something like HA. I want to multiply to beta H. Then their product is given in the following way. Look here. So this H acts on X. So what I can do, I can add here the so-called left shift of this. So I take this map beta, but twist it with element H, and then I have two maps from X to G and here from X to G, and then I define this in the following way. So here will be gamma H multiplied by H prime, where gamma of K of X is defined by the following formula. So I need to take alpha of X and multiply by beta on HX. So this is like direct product, but not. It is almost direct product in some way. So I act by this H on this beta. And this set with respect to this multiplication is actually a group. It is a well-defined group, and it is called the wreath product of G and H over the action of X over the action of H on X. Maybe they look. Maybe they look complicated, but actually wreath product were introduced, and in the literature they first appeared in the paper by Camille Jordan. This is the same in 1869. This is the same Camille Jordan, which we know the Jordan normal form of matrices. He is also proved invented by him, as well as the well-known theorem, Jordan curve theorem, that every closed curve on a real plane bounds to disk. So there is a homomorphism which maps this maybe picture of very strange form to the unit disk. Well, and now this wreath product also appears. Why they are important? There are two things in which they are very important. One of them is we have if you have a group and here is the so-called group extension. So what does it mean? That we have here is inclusion, and here A can be viewed as a quotient. Then actually, then there is always there is always an inclusion of this group into the wreath product of B and A. I will define now what's it, and here just maps from B to A. So this is the result of collusion, that every wreath product, every group extension actually is a subgroup of this special kind of. So every group of this kind is embedded into the wreath product of the kernel and the quotient. And therefore they have importance because they, in some sense, they contain everything. Now, another, and let me define what is the wreath product of two groups, just two groups. So if I have a group G, if a group B and a group H, a group B, then B acts on itself by multiplication. So just it acts on itself by left shifts, and the corresponding wreath product of B A over B over the action of B on itself is defined by, is usually denoted by these letters, and is called the regular wreath product. Regular wreath product. Now, about actions of this set or of this group on some other spaces. Actually, usually, if suppose we have a group G which acts on a set X, and also group H which acts on a set Y, then there is a natural, and just for simplicity, assume that H is a finite group. H is finite group consisting of M elements. So I can enumerate elements of H by H1. Okay, just can enumerate all elements from H by numbers from 1 to M. So the group contains just M elements. Then, if I consider the following set, I do the following: X to the power M multiplied by Y, and there is a natural then the group, the wreath product naturally acts on this set, on this product by the formula which is very similar to the previous action. Let me define how it acts. So what is the G wreath H? By definition is the set of maps from H to G. So sorry, here is H. But what's this? This is the set of maps from finite set of M elements to G. And actually this can be just identified with G to the power M. So so this is just G to the power M. So it is a set. It is a direct product of G to the power M with H, and here we have some operation with multiplication which is similar to this one. And there is a natural action of this group on this set by the following formula, which is close to that. So if I have G1, Gm elements, and also element from here H, then it acts on this set. So I take just M element and Y, and this is like it is very similar. What I should do, if it would be a direct product, then I just act by each Gi on the following X on the same Xi. But now, since H acts on itself by left shift, then actually it acts on indices. So H acts on this space because it has M elements, the same number as elements in H. Then it acts on it by permutation of coordinates. So I do the following: I act G1 will act on X H of 1. Let me denote that H of 1 is just the corresponding coordinate and here G2 acts on A or H2, and so on. And finally, the final, okay, GM acts on H of M, and here H acts on Y. This is this action is what is the natural action of the group of the rest product on this on this product. And it is also what can be proved about. I will do several will present several examples now, but let me say a few words about this. First of all, if G acts on X and H acts on Y are free actions, let me say, and here, or maybe even more generally, for example, if or the projection maps from X to XG and the Q from Y to Y to the quotient are covering maps, if either of conditions, here is a more general thing that we need also so free and properly discontinuous action, not just to have free actions. Then each of these conditions imply the same property for the action of G res I on this. So if they are free actions, then this action is also free. And similarly, if it is a covering maps, then the corresponding then in this case x m y to the x m y to the quotient R is also covering, and this free. This kind of actions are very important in some cases in homotopy theory, because why it is important? For example, if pi1 x and also and pi1 y are 0, or even these spaces are contractible, y contractible, then each of them implies that pi1 of x m y or and x m y is also 0 or is also contractible. And at least what does it mean? This implies that fundamental group of the quotient is isomorphic to GH, because if in these cases we have, for example, if we have a covering map, then this map, if these spaces, if here are covering maps and x and y are simply connected, then this map, this space is also simply connected, and this is a covering map, and therefore this is a universal covering map. And since it is universal, the fundamental group of this quotient is isomorphic to group which acts on this space. Moreover, if they are contractible, then this space is also contractible. But contractibility here, together with free actions, means that X by G is what is called a classification space for this group. And the same X and Y by H is also the classification space of X. And from here, this implies that X, M, Y by this quotient is the classification space of G, G res H. And so sometimes what is important thing, that this quotient space, all in homotopy theory, it often studied as a it is a model for the classification spaces of rest product. But where is the problem appears in the following point. So suppose that X and Y is non-zero and pi1, Y is also non-zero. So if the spaces on which act GH are, suppose we have a covering maps, but actually these spaces are not simply connected, then the question, what is the fundamental group of this quotient, is looks rather complicated, because here we just use here when we have covering maps and they are contractible, then we have a general statement from the theory of covering spaces. But in general, there are no convenient ways of computing these things. And the problem is, because if you want to compute the fundamental group, then we have only so we have just, if for instance this covering is this map is a covering, then we have only short exact sequence. So here will be to the power m by pi1 y. Here is pi1 of this quotient which we are interested in, and here will be the group GH. So this is a very special extension, and the question is, what is the algebraic structure of this group? Is it requires additional work. And with my result, what I present here, I give precise expression of this group in terms of the fundamental group of the corresponding quotients. So we can exactly compute this group if we know this the fundamental group of these quotients. And this has some applications to the study of to deformations of smooth functions on surfaces. And I will say about this in the end of the talk. So let me formulate what is the general statement. Suppose we have two actions, gx on the set, a group gx on a space, a topological space x, then hx on a topological space y, and the quotients x to xg and q y to yh are covering. Then the fundamental group, then we have a natural action of the wreath product on this, and also let me assume that the H has exactly m elements. Then the fundamental group of this quotient is isomorphic to the following things, and I will first write this down, and after that I will explain. It will also be a wreath product, but in some special wreath product. Namely, this will be the wreath product of the quotient. Here I write, and here I put boundary y, and I will explain what this with pi1 of yh. So this fundamental group is also a wreath product, but with respect to very special action, and this action is not effective. What is this action? So it is not effective action, and namely, what's this? What does it mean? Recall that we have since Q is a covering map. Our Q is a covering map. Then we have a short exact sequence of fundamental groups of homotopic groups of this covering. Namely, we have a map from pi1y to pi1h. Here is an inclusion, and here is a surjection to the group H. This is a standard short exact sequence of the covering map. And here is a homomorphism A. Here is a boundary homomorphism of this covering. So I just let me recall, if this is a y, and here is say some point y, and here are its inverse images pi q minus y of y. Then if I have any loop here, take any loop gamma, then and take here any point, then if I take a lifting of this loop, then I will get some path which starts at I take here point, some fix some base point in the inverse image. Then liftings of path of loops here correspond to passes which start at, okay, we start them at the same point, but they finish at distant points of the inverse image of y. And there is a natural, but if, for example, if pi1 is so the idea is that there is a bijection between the inverse images of this point and the set of adjacent classes of this quotient of fundamental group of the quotient on the, he is h and he is y, sorry, on the fundamental, by the fundamental group of this. And actually, if this cover comes from the action of H, then actually this is a normal subgroup and the quotient is naturally isomorphic to H. So we have a homomorphism, this boundary homomorphism. And now I can define, using this homomorphism, I can define this first product in the following way. Namely, this pi1 x g h and he is pi1 y h is defined as the set of maps from the group H to the group pi1 H by G. So this is the set of, this is both of them are groups, but I consider them, just maps. So they are not necessary to be homomorphic. And then I take this, then the group pi1 y this quotient naturally acts on the group H via this homomorphism. So I can multiply. So if I have element gamma belonging to pi1 y and I have H belonging to H, then I can multiply gamma by H. By definition, this will be the following. I need to take boundary apply boundary homomorphism to this gamma, and after that I get an element from H, and after that I can multiply them in the group H, and this will be the correct action. And by definition, this wreath product is the following group. So it is a wreath product of the group of this group H, wreath product of the it is a set of maps from this group H to the fundamental group of this quotient, and the wreath product with the fundamental group of another quotient. And the statement is that this group has this precise algebraic description. Let me consider several examples, because maybe it looks like very formal and okay, example. See, the most simple examples which let us take the action of the group G, say 3, on the circle, and another, say, the group the same, the group Z4 on again on the circle. So this will be Gx on H on X, and this H X on Y, and after that, what is the wreath product of GH? This is by definition is what is, I need to take Z3 wreath product with Z4, and this group is by definition the set of maps, or I can even take, so what I should do, I should Z3 to the power 4 in a wreath product with Z4. And multiplication here is the following. So if I take 4 elements, A0, A1, A2, A3, each of them it takes values in this group, so it is 0, 1, 2. Then also I take an element, say K, which takes values 0, 1, 2, 3, and multiply it by B0, B1, B2, B3, and L is equal to the following. What I should do? I multiply them, but first I need to cyclically shift these elements by K. So it will be A0 multiplied by K, then AY multiplied by K plus 1, A2 BK plus 2 and A3 be k plus 3, and after that I also multiply k plus L, and here I take the modular in the group 4, the modular 4. So this is a multiplication. This is multiplication in this direct product. And now consider the action of this group on which space. So then this group acts on which space. So I need to take x to the power 4 because I have here 4 elements on y. And this means that I take the circle to the power 4 multiplied again by circle. So what is the interesting, if we consider only the actions of cyclic groups on the circle, then I always have an action of this group on the torus. And now this action is given as follows. So if I have again element y0, a2, a3, and k, and x on element, say, here, I regard as a circle as a set of complex numbers in the complex plane. So x0, x1, x2, x3, and some y. This is also complex number. Then it is given by the following formula. So a0 is just a rotation. So I need to, and what I do, I make a rotation by a0. So and a0 is rotation by this group is of order 4, so it is generated by rotation by pi divided by 2. So it is 2 pi i a0 by 4 and multiplied by xk, then e to the power 2 pi I a1 again divided by 4 and multiplied by x plus 1, and so on the same. And finally I need to act on this this k should act on this y, and this will be e to the power, now k belongs to, oh sorry, here I divided by 3 because a0 they from this, oh here by 3, but and here 2 pi I k multiplied by 4 and y. So it is just rotation. So it is a 5-dimensional torus, and the action is the following. So we first rotate the last coordinate, and the other coordinates are first cyclically shifted, and after that I rotate each of them independently by this angles. This is an example, and why it was important and appeared, why it is why I started to compute it. It appears in the following situation. So suppose we have M is a compact surface. Compact surface. Let me just consider some examples. Something like this. And consider a smooth function from M into R. Suppose it is a Morse function. I will not be talking about this, but assume that it has a finite number of local maximums, finite number of local minimums, and finite number of some saddles. Well, this is a function of this kind, so it can be arbitrary function. And it is known that the space of Morse function is everywhere open and everywhere dense in the space of all smooth functions. So I have this function. My function will be the projection to this vertical line. Then there is a natural action. The group of diffeomorphism of this M naturally acts on the space of smooth function on M, and it says acts by the following formula. So if I have a foliation, you see, like singular foliation by these curves, and if some of them are not so here regular level sets corresponds to are circles, and the critical level sets are just some graphs. There is we have this foliation, and then there is a natural action of the group of diffeomorphisms on this space. Namely, if I have a function f, here is a diffeomorphism in the function, then I associate with this composition. This means that what actually geometrically, this means that I have a foliation, and each leaf of this foliation also remember also remember the value. So at each level, it assumes that it is written the number. And diffeomorphism makes this picture, so it deforms this picture in some way. But we remember the numbers on the images of this curve. And this gives us another function, which is just a composition f with this a. And here is a natural, okay, it's the right action, but I wrote diffeomorphism from another side. And there was more than about 15 years, maybe, studying the homotopy type of the orbits. So if I have a function, then I can consider the stabilizer of this function with respect to this section. So this is a group of diffeomorphisms which preserve my function, and also the orbit. It is the set of functions of this kind. And there was a question was about homotopy type of these spaces. It was computed. I will also be not talking here, but the final statement, which is so it was computed by me and also by Elena Kudryavtseva. She independently obtained the results about this, and also by Bogdan Fishchenko and the key mathematician from our institution, Bogdan Fishchenko, Yulia Soroka, Irina Kuznetsova, Anya Kravchenko. They also take part in this kind of computations. And the general result which was obtained, the final problem was reduced to the computation of the fundamental group of the orbit. And it was proved that the set of, if I consider the class, let me say B, of group of fundamental groups where F is for instance, Morse function. The class of fundamental groups. So what is the structure of these groups? Then it turns out that this class is contained, at least contained in the groups, in the class of the following. Consider two operations over groups. So let say P be the minimal class of groups having the following properties. First of all, it contains unit group, okay? It is closed with respect to, if A and B belongs to P, then it closed with respect to direct products, and also closed with respect to the following rest products, namely if A belongs to P and N is just some number, then the rest product A Z with respect to the action. So I put here N, and this means I take here N times multiply, this is a with Z, and Z acts on this set by cyclic shift of this of coordinates. So it is essentially non-effective action. And actually this appears, so for example, then it is required that the group belongs to P. It appears from the following picture. So suppose we have AX on some set X, and such that the map is a cover. then and also I have the action of on the circle by z n. This is just a rotation. Then this group A is the same as in the theorem. So it is obtained by the boundary so this action appears from the boundary map of this of the fundamental of the homotopy groups of this covering map. And the statement is that what was the statement? That B, the class of this fundamental group, is contained in P. So I just 1 minute. I will stop. This was the general statement, and was there was a conjecture that the fundamental, that the orbit, the connected component, the orbits are they are aspherical. So their fundamental groups determine their homotopy type, and it was proved by Elena Kudryavtseva, first by me, but for generic Morse functions, and in general by Elena Kudryavtseva, that the orbit has a homotopy type of some torus and of some dimension with respect to the action of some group G, finite group G. So there is a torus finite group which freely acts on this torus, and the orbit is homotopy equivalent to this space. And I obtained the result which gives precise algebraic structure of this group. And in particular, I proved that it belongs to this. So every fundamental group of that kind belongs to this class. And the problem is to prove the homotopy equivalence. To prove that there is a homotopy equivalence, it can be proved by, so I represent every group of this kind as a composition of these operations, and this result allows to identify, to prove that the fundamental group of, so actually if A appears from the action of on some torus, then this group is also the fundamental group of some of the action of some other group also on the torus. And so finally this allows to make another proof of this statement. Okay, maybe so I will stop here. So thank you very much.
Thank you very much. Questions, comments, please.
I have one question. Oh, sorry.
Yes.
Maybe. Yes, I have one question connected with structure of this complex of gamatopy groups, which you called minimal close of groups. Значит, collection of these gamatopy groups, which are P. You name it P. B is enclosed in P. It is right side of your slide. Yes. And can we say that these gamatopy groups could be included one into another as nesting of some figures? Because every closed maybe a torus be divided into some in spheres, production spheres, so we can consider production of gamatopy groups, and can we consider as such nesting, or maybe no?
Yes, it is clear from here that A, for instance, is a subgroup of this. Yes, they are included in each other. But actually, maybe it is more to understand what is minimality means. This means that groups of this kind. I take Z, then say the action of here I put 5. Here I can multiply by again z in some power 7, then I can take rest product of that kind, 9 with again with z, then I can do a lot of operations of this kind, and every formula of this form, it belongs to this class, and for every such formula I can even precisely realize a concrete to present concrete function on a surface, on at least on the disk, on the surfaces which whose fundamental group of whose orbit is precisely this one. So it is, yes, there is some hierarchy or some, but it is better, can be better viewed in via these formulas. And they are clearly, there is a clear action of this kind of group. So using them, we can precisely write actions of some other groups on the torus corresponding, so that the fundamental group of the quotient will be of this kind.
You can take any other degrees, sub-degrees, and so you will consider
everything. Yes. Okay. And everything can be realized and even explicitly describe how it acts.
Okay, thank you.
Andrei, please, are you?
Yeah, so my question is, I mean, I would say, maybe easy to answer. I suggest, so you have a very explicit formula for the fundamental group of your quotient. So you quotient your product x times m times y by the wreath product. Of course, having the fundamental group, you also have the first homology group because it's abelianization of your result. My question is, can you give a formula, explicit formula of the first homology group, which uses only the homology groups of the quotients? Yeah, so yeah.
It's thank you very much. Very interesting question. And at least for the class of this group, it is just Irina Kuznetsova. They will be Irina Kuznetsova and Yulia Soroka. They will have a talk just today. And okay. They have, maybe they will be talking about this, but they prove the general statement is that the homology group of this, so if you have this fundamental group, then the homology group of this is just the number of letters Z, the rank, the Betti number. But in this case, this is a very interesting question, whether in this situation we can explain. I need to think. This is another problem. And the problem is that we need maybe to use something like spectral sequences because there is no homotopy groups are related in very simple way. For vibrations,
yes, you have Lie spectral sequence.
Yes. Yes, thank you very much. I will think about this. Thank you.
Okay.
Thank you very much.